Hey guys, so today's video will be on torque and rotational dynamics. So without further ado, before I get started, I'm going to just do a quick recap on the three kinematic equations, and you'll see why in a minute. So the first one is that speed or velocity is equal to v naught plus at, and the second one is the second one is that the position as a function of time is equal to the initial position, and it need not necessarily be the x position. It could be y or z. I'm just showing x as an example. But it's the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. And lastly, we have that the velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And keep in mind these only work if your acceleration is constant, and if it is not, then you have to resort to calculus. Okay, yeah, so these are for like linear motion, right? Or it's, in other words, translational motion. And likewise, we actually have another set of very similar kinematic equations for rotational motion. And so the first one is omega is equal to omega naught plus alpha times t. The second one is theta, or theta as a function of time, is equal to the initial angle, which is theta obviously, plus omega naught t plus 1/2 alpha t squared. And as you can probably guess, the final one is omega squared is equal to omega naught squared plus 2 alpha delta theta, where this is just the angular displacement or the change in angular position. And just like the translation ones, the translational equivalent, this one also works only if there's a constant angular acceleration. So from here onwards, if I say acceleration without any angular in front, it's implied that it's translational. In other words, it's linear, but we typically use translational. And as you can probably deduce just from looking at the similarities of these equations, we know that omega is just angular speed, or in the context of a simple harmonic motion like pendulums and stuff. I'll get to this later. It can also mean angular frequency. But as far as we're concerned for now, it's angular speed. So yeah. And as you can probably guess, theta is just angle or angular position, which, well, yeah, that's pretty much angle. And I'm just calling it position because it's just to show that it's like the equivalent of this, albeit in rotation motion. And lastly, we have alpha, which you can probably guess, and I already said it here, but it's angular acceleration. So yeah, so basically these are the three kinematic equations, and this is for the three kinematic equations for translational motion, and this is the rotational equivalent. So yeah, that's interesting to note. So another thing that's important is actually that there are ways to go from translational to angular and vice versa. So basically, we can actually drive it. So let me just scroll here. Okay, so let's say we have a circle, and that was kind of poorly drawn, but it's a 5. It's good enough. Okay, so Let's say we have a sector here, and we know that. Let's say we know the quote unquote circumference. Well, it's not really circumference, but like this length here. So let's just call it S, because S is actually, it's called arc length. So S is arc length. And let's say we want to find theta. Well, the formula is just that S is equal to R theta. So similarly, if something travels from here to here, and we know what the angle is, so it's some angle theta, then we can just find how much displacement is using the above formula. And it's kind of redundant to write it twice, but whatever. So, yeah. And likewise, since we have, okay, I'm gonna write it again. I don't know why I erased it, but since we have S is equal to R theta, we can see then, so if we take the derivative of both sides with respect to time, we get this. And the change in length with respect to time is, or change in displacement with respect to time, or is just velocity or speed. And this is just d theta dt is just the angular speed. And we get this. And finally, we have, what was I going to say? Oh, yeah. If we take the derivative of this one more time, or the derivative of this, we get dv dt is equal to r, and we're not taking the derivative of r because it's constant, but r d omega dt. And this gives us, or this implies that the acceleration is just r times alpha. And another cool thing we can derive using these is just that not tangential. Centripetal acceleration, actually there's no m there, that's centripetal force. The centripetal acceleration, which is v squared over r, can now be rewritten as omega squared times r. Also, there's another thing that's important to note. This only works in pure rolling motion, because so there's basically, with things like wheels, there are three types of motion: translational, pure rolling, and a combination of the two. And I'll talk about this later in this video. But for now, I'm going to move on to an interesting concept known as moment of inertia. Wait, just keep in mind that these only work, so these three equations, so this one too. So S equals R theta, V equals R omega, and this only work in pure rolling motion. Okay, so with that being said, the next topic that I would like to discuss is torque. And actually, before I discuss torque, another important topic that I need to introduce before I can even discuss torque, okay, that's what I just said, but whatever, is it's called moment of inertia. Okay, and the symbol is just an I, and some people also call it rotational inertia, but this is the official name. So basically, to discuss this and to understand this easily, we have to first talk about mass. So we know that if we have an object with a given mass, to make it change its motion, in other words, accelerate or decelerate, we have to apply a net force on it, obviously. And this is for translational motion. So mass, in other words, sort of resists the force, because the more mass you have, the less of an acceleration a certain force is going to cause. And similarly, we have the moment of inertia, which is the rotational equivalent of mass. So if you want to get something to rotate, the higher the moment of inertia, the harder it will be to make it rotate. And the more torque you're going to need. And torque is just the rotational equivalent of force. But for now, I'm going to talk a bit more about moment of inertia. So basically, mass is a resistance to change in motion, and torque can be thought of, or sorry, moment of inertia can be thought of as a resistance to a change in angular motion. Okay, so a formula for moment of inertia is actually, because this one is a bit trickier in math, because you actually have to calculate it, but it's m sub I, okay, m sub I, r sub I squared, and yeah, that's one of the formulas. So what do these mean? M sub I, so this formula it's meant for certain situations. So it's this formula is meant when you have like an axis of rotation and you have several masses around it. So an axis of rotation is just something which you rotate something about. So for instance, if I have a wheel rotating, the axis would go like through the wheel since it's rotating around it. And so this is when this formula works. It only works if you have like an axis of rotation and you're trying to get like several objects around it. And they're usually point masses. And so m is obviously just each individual mass, and r is known as the moment arm. It's basically just the distance between the mass and the axis of rotation. Okay, so just as an example, if I have some point masses, let's say this is 2 kilograms, 3 kilograms, 4 kilograms, and just let's say this is 1 meter. This is also 1 meter, and this is 2 meters. Well then, the moment of inertia or rotational inertia would just be that formula which I put above. And it's actually kind of similar to the center mass formula, so it's important not to get this confused. But yeah, so the formula is, so for this mass we have 2 times 1 squared. For this one we have 4 times 1 squared. And lastly, for this one we have 3 times 2 squared, which gives us 2 plus 4 plus 12, which is just 18 kilograms meters squared, as you can probably tell from this. So this is if you have several point masses. Now what if you have like some long mass? So let's say I have a rod, and let's say it's rotating about its center. So then the axis of rotation would be like this. So how would I find the moment of inertia of this? Well, there's actually a formula for that. So for a continuous mass distribution, the formula for moment of inertia is just r squared dm. And this one's a little bit trickier because there's a bit of calc involved. And r also means moment arm in this situation as well. Dm is just an infinitesimally small part of the mass. So let's say that this rod has length L. So since this is the axis, let's say we have an x-axis as well, and this area here is L at the x-axis. This is 0, and this is negative L. Well, then we can just integrate from negative L to L. And if it has a constant mass or linear mass density, so that's denoted by lambda, and that's equal to dm over dl, or also m over l since it's the same throughout the rod, then we can see then that dm is just equal to lambda dl. So then we can rewrite this as lambda from negative L to L of r squared dl. Okay, and then since this is all in the x direction, we can actually change this a bit. So we have lambda is equal to negative L x squared dx. And this is just basic integrations. Then we have lambda again times 1/3 x cubed from negative L to L. Okay, so then we have 1/3 L cubed, and this all multiplied by lambda. So 1/3 L cubed plus 1/3 L cubed. And then since lambda is m over L, we have m over L times 2/3 L cubed, which is 2/3 L squared. Sorry about that. Oh, actually, you know what? Okay, my bad. This is should be L over negative L over 2. This is L over 2. Since this whole thing is lambda L, so that changes things a bit. So then this would be 1, not 1/3, 1/24. Should also be 1/24. Okay, and then this would be 2/24. So this would be 1/12. So we have 1/12 L squared. So for any rod that's being rotated like this about its center, the moment of inertia is just 1/12 L squared. And yeah, so basically what the point I was trying to get across is this is the formula for a continuous mass distribution. And usually it's instead of having to derive it manually, it's just easier to remember the oh wait, okay, also made another mistake. It's 1/12 ml squared. I almost missed that, but fortunately I didn't. So 1/12 ml squared. So yeah, generally it's easier for it's just easier to memorize it than just taking the time to derive it like on a test or something. And yeah, so okay, so this, as said earlier, is only for point masses around a continuous charge distribution, and this is for, or sorry, around an axis of rotation. This is for continuous charge distribution. So any rod, and this is a universal formula. So you just plug in the mass and the length for any rod, which is in this sort of position. Now, the tricky thing about moment of inertia is, unlike mass, it's not an inherent property of an object. So for instance, if I had some mass that was 2 kilograms, it doesn't matter how I orient it or what planet it's on, it's always going to be 2 kilograms. But for rotational inertia or moment of inertia, it depends on like what it's being rotated about, like where the axis of rotation is. So just as an example, let's say I have the exact same rod and its length L, but this time it's being rotated about one of its ends. So it's rotated like that. So this time the integral would be a bit different. So as I said earlier, the formula is I is equal to r squared dm, which is just lambda, and I'll say it's x squared since most of the mass is on the x-axis, or all of it is, x squared dx, and this time the bounds are different, so it's from 0 to L. And so if we integrate it, we have lambda times 1/3 x cubed, which gives us m over l, m over l, my bad, because that's lambda, times 1/3 l cubed, which then gives us 1/3 ml squared, which is different from this 1/12 ml squared. So the point I'm trying to get across is it's a bit more tricky to deal with than mass. Like one object doesn't have a given, like one single given moment of inertia. Well, it has a single mass. And the moment of inertia depends on its orientation and how it rotates. So yeah, and another important thing to note is if you just look at this formula or this formula, you can already sort of deduce it. But the further away the mass is distributed from the axis of rotation, or in other words, the higher the moment arm is, the greater the moment of inertia. Or in other words, the more resistance there is to an object rotating. So, for instance, here we see our formula is 1/3 ml squared, but here it's 1/12 ml squared, and that makes sense because more of the mass here is closer to the axis of rotation. So then, it's expected that we would have a lower value, but here more of it is away. Sorry, my throat. Yeah, okay, sorry about that. So yeah, another example is if we have a sphere, and I memorized this, and I'd recommend memorizing as well. But for a sphere, the formula is 2/5 m r squared. But for a spherical shell, so in other words, like it's empty except for the outside, the formula is 2/3 m r squared. And the reason is because more of it is distributed further away, so it's harder to make it roll. And so, as I said earlier, it's better. You're better off memorizing the individual ones for each shape than just having to take the time to derive it. It's just a huge waste of time. So, I'm gonna give some of the basics. So, as I said earlier, a stick around the center is just 1/12 ml squared, where the stick is the length. So, you can just plug in the mass and the length if it's given. And as I said earlier, around one end, it's 1/3 ml squared. Oh, and keep in mind that these are all assuming that mass is uniformly distributed. So, yeah. Okay, a ring around the center. So, it's like this. Okay, I shouldn't have drawn it through, but you get the idea. It's mr squared, where r is the radius. And a ring where the axis of rotation is around the diameter. So, it's like this is 1/2 mr squared. Similarly, for a disk where it's going through the center of the disk, so that the rotation is like this, and the axis rotation is going through the center, it's 1/2 mr squared. And if you extend the disk, you also get a cylinder, and if the cylinder's axis rotation is going through it, it's also 1/2 mr squared. So you can think of a disk as a compressed cylinder. Now, if you have a disk and it's going through the diameter, so it's rotating like this, then it's 1/4 mr squared. And if you have a cylinder, okay, if you have a cylinder and it's going through, it would be 1/4 mr squared plus 1/12 ml squared. And you might be wondering, what's the difference between this and this? Well, you would use this if it's like really thin and you don't really care about the radius. Like the radius is negligible. If it's not, then you would use this formula. And yeah, so these are just the basic formulas, and you're better off memorizing it for tests and stuff. And yeah. Okay, finally, for moment of inertia, there's also two important theorems. The first one is the parallel axis theorem, and it states that the moment of inertia is equal to the moment of inertia at the center mass plus the mass times the distance from the center mass squared. And it's useful in deriving the moment of inertia for like for axes of rotation that you're not familiar with. So back to the rod example, let's say we're going through the center. And we don't know what the moment of inertia is, but we know that the moment of inertia through one of the ends is, as I said earlier, 1/3 ml squared. Actually, no, it only works for center mass, so it's actually the other way around. So let's say we know here it's 1/12 ml squared, and we want to find what it is here. So we know then that this second axis of rotation is here, and the total length of this is L. So this distance here is L over 2. And so we can plug it into this formula. Since we know that this is 1/12 ml squared, we have that I is equal to 1/12 ml squared plus m times L over 2, which is over here, L over 2 squared, which gives us 1/12 ml squared plus 1/4 ml squared, which is 1/3 ml squared, which checks out with what I said earlier. And yeah. Another important formula to know, well, it's not as important, but okay, so this is known as parallel axis theorem. And yeah, you can see why it's called that. It's pretty self-explanatory. And we also have another formula known as the perpendicular axis theorem. And so this states that I sub z is equal to I sub x plus I sub y. And as you can guess, each of these represents an axis. And this only works, it's important to remember this, it only works for planar objects. So, like, basically two-dimensional stuff. So, for instance, let's say we have a disk. And as I said earlier, the formula for a disk through the diameter is just 1/4 mr squared. And let's say I want to find, or I want to derive the formula for a disk when it's through the center. So we would call this, let's say it's um, a certain axis. So let's just call it the x-axis. And it honestly doesn't matter what you call it. What matters is you have to add up two of them to get the third. So in this case, this is called the x-axis, and let's call this one the y-axis. Well, we know that here it's 1/4 mr squared, but this is also the diameter. So here it would also be 1/4 mr squared. So then if it's going through the center, it would be the sum of these two, which would mean then we have 2 times 1/4 mr squared, which is 1/2 mr squared, which checks out. I mentioned it earlier, and yeah, it's 1/2 mr squared. And so this one you won't see as it's not as important as the first one since it only works for flat objects, but still can be useful at times. And this one's pretty useful, especially if you forget like one of the formulas. Okay, and then so there's also rotational kinetic energy the same way that there's translational kinetic energy. And if you recall, for translational kinetic energy, the formula is 1/2 mv squared, and for rotational kinetic energy, it's 1/2 I omega squared. So yeah, and if an object is both rotating and moving in a translational way, then the formula would just be these two added up for the total kinetic energy. And if it's just rotating, you would use this, and if it's just translating or moving in a linear path, then you would just use this. Okay, finally we can talk about one of the most important concepts in the video. I mean, everything here is pretty important, but we're going to talk about torque. And so the formula for torque is that it's equal to, well, there's several formulas, but the first one I'm going to talk about is it's equal to the dot product between the moment arm and the force. And I think in my magnetism video I briefly discussed dot products, but yeah, this is the first time it shows up in my mechanics series, I believe. And remember that for dot products, or sorry, not dot products, cross products, the order matters. So this R has to come before this F. And if you're new to cross products or you don't know what it is, well, basically how it works is so there are three axes. So normally this is called the x-axis, this would be the y-axis, and this would be a z-axis. But in vector like stuff, we would call this I hat, j hat, k hat. And so basically, how torque works is that or cross products in general, I hat times j hat is equal to k hat. And you can, and basically the whole idea is this thing called the right hand rule. And basically, I talked about it briefly in the magnetism video, but basically, I can't say basically a lot, but the first term here, so I'll call this factor 1. This is represented by your index finger. And this term here, which I'll call factor 2, is your middle finger. And this product here is your thumb. And basically, to find the direction of the torque, you'd basically have all three of those fingers perpendicular. So you'd have, yeah, it's kind of hard to draw them perpendicular, but you'd have them so that they're sort of like the axes. So they're all perpendicular to each other. And so you'd point your middle finger in the direction of R, the force in the direction of, well, the force, and then wherever your thumb would be pointing would be the direction of the torque. And so, okay, this is an example. Let's say I'm closing a door. Yeah. Okay, so then I close the door, and we know it would move this way, right? So now I'm pushing forward, and I'll denote that by an X. I mean, that is how you're supposed to show that it's going into the screen or into the page. And you can think of the X as sort of the fletchings of an arrow. So if you're shooting an arrow into the page, then this would be what the X represents. So that's where my force is going. And R represents the moment arm, and that's a vector that can go from the axis of rotation, or in this case where the hinges are, to where the force is being exerted. And so it goes like this. So this is R, and then this is F, and it's going into the screen, not up. So then if I use my index finger for F and my middle finger for R, actually sorry, no, index finger for R, okay, because of this order here. It's important not to forget that. I almost did. Okay, so index finger for R and middle finger for F. We get that the torque would be going upwards. And so yeah, that's how you'd use cross product torque. And so because this is how the formula for torque is a vector, torque, or the magnitude of torque, is just R F sine theta, where theta is the angle between this and this. And so we can see that it depends on three variables: the angle, this, and also the force. And this actually makes sense with how doors work, because if you have a door, and if the knob is like close to the hinge, then we can see that our moment arm would be super low, and so we wouldn't have a high torque. On the other hand, if it's at the edge, which it should be normally, then we can see we would have a high torque. And yeah, so that's the basic. Those are the basics of torque. Okay, and so as I mentioned earlier, I is basically the resistance to torque, and so it can be thought of as the sort of rotational equivalent of the mass, which then means or makes sense for torque to be the rotational equivalent of the force. And torque is also in Newton meters, so that's the units for torque. And you can sort of see that just from looking at the formula. And so, in the same way we know that F is equal to ma, and I know I made a whole video on why this isn't always true, but um, we have a similar formula for torque, where torque is equal to I times alpha, where alpha is the angular acceleration. So we can already see some similarities. And the other better formula for force I talked about in my previous video is F is equal to dp dt. Similarly, for torque, we have that it's equal to dl dt. And we can actually use this to show the law of conservation of angular momentum, the same way this shows the law of conservation of linear momentum. So in the same way we have mi vi is equal to m sub f v sub f. We have I sub I initial times that is equal to this. And so an example of the law of conservation of angular momentum, and if you have the material to do this, I'd highly recommend trying this. But if, like one thing ice skaters will do is when they're spinning, they'll have their arms out. And that means they have a high moment of inertia. But then they'll draw their arms inwards, and they'll lower their moment of inertia. But that will also increase their angular velocity, or their final angular velocity, in order to conserve angular momentum. And yeah, so that's interesting. And yeah, so as I said earlier, there are three types of rotational motion, or motion in general, I guess. So let's say we have a wheel. The first type is called pure translational motion. So basically, there is no angular velocity, so it's just sliding on the ground. And the velocity everywhere is the same. It's equal to the velocity of center mass, which is here. And so I'll call this pure translational. Okay, next one is pure rolling, or pure rotational. Okay, if it's pure rotational motion, what that means is that the center mass is not moving, and it's basically just rolling in place. So there's some value omega, and here we have some instantaneous speed, which is equal to v is equal to r theta. Well, the whole thing actually is at speed v is equal to r times omega, not theta. And yeah, so as in fact that goes back to actually mentioned that earlier. So where did I put it? Oh yeah, here. So this only works for pure rolling motion or pure rotational motion. And yeah, and the third type is so oh yeah, here it's also moving, but it's moving the other way. Also at v is equal to r omega. And yeah. Okay, and finally our third type is just a combination of the two. Okay, and so we have our center mass, and we have, for now, we're going to look at these 3 points. So if we add all of these up, we can see that these would cancel out because this is going at v, this is going at v, and because this is a combination of these two, we can just add them up to see how it works. So here, the velocity would be equal to 2 times r times omega, because now you're also factoring the translational speed. Here, it would be just the center mass would just be r omega. And here, it would actually be instantaneously still. So it would just be 0. And so if I were to draw arrows throughout, it would look sort of like this. And here, it would just be the same. So basically here, it's above where it is at the center mass. Here, it's below. And this is what we see in cars that are moving, like normally. So here, it's actually 0. And the reason why is because these two cancel out. So even though the wheel is rotating to the left, or it's rotating clockwise, the whole thing is moving to the right at the same speed. So overall, the speed relative to the ground is 0. Well, here it's like double. So it can be a little confusing at first. And some examples of each of these, I guess, would be, this is just normal car motion. This would be like if you're on ice, so there's no friction that causes it to roll, or no static friction. And here it would be, I guess, if you're like stuck in mud and the wheel is rotating but the car isn't moving anywhere. Or if you're like against something. And so yeah, these are the 3 types of rotational motion. And how rotational motion works is actually, so, well, I forgot to mention, so here you would use k is equal to 1/2 mv squared since there's no angular velocity. Since there's no translational velocity here, you use I omega squared, and here you would add up the two. And yeah. Okay, so then here, well, we can say, oh yeah, okay, so how a car works. So let's say we have the cars moving this way. So the wheel would be rotating this way. But then it hits the ground at this point here. And so the ground exerts a static friction on the wheel. And that causes the whole thing to move. And then this part of the wheel hits the ground. And then the ground again exerts the static frictions, and so on. And that's what causes the wheel to move forwards. And yeah, so those are pretty much the basics of rotational motion, so torque, moment of inertia, and then I briefly talked about angular momentum, which is this, and yeah. Oh, yeah, and also you can find a formula for work. So in the same way, work is force times displacement. It's also equal to torque times the angular displacement for rotational motion. So yeah. And so with that being said, I hope this video helped, and thank you for watching.